Greetings and welcome to my second of two videos in which I try to explain how to bias double-ended amplifiers. In this video, I'm going to actually demonstrate the biasing process of a double-ended amp using the output transformer method of determining plate current rather than the bias resistor method. I will explain to you why I think it's a better method. Although the cathode bias resistor works, this is actually a little better in cases especially when the plate current is different, when the tubes aren't well matched. And thirdly, I will discuss with you briefly how to adjust the bias on amps that are grid biased and have the cathodes grounded. If that sounds of interest, then stay tuned. We're about to begin. First off, I prepared a worksheet where I can write down my results in a orderly fashion so that I don't get mixed up. As you can see from this chart, I think this is a decent way to do it, and then keep this in a file with the schematic of the amp. I'm going to designate the two tubes either outer or inner. The outer one is near the edge of the amp, the inner one will be near the center. If you say left and right, that can change depending on how you orient the chassis on the work table. First, we'll measure resistance pin 3 to pin 8. That will be the 1/2 of the output transformer winding. We're going to find out what the resistance is. Then we'll switch and find out what the resistance is for the other half of the output transformer winding. We'll measure the voltage drop across each of those resistances. We'll calculate the plate current by dividing the voltage drop by the resistance. We will measure the plate voltage directly. And I'm going to show you safe methods to do all of these procedures. And then finally we'll calculate the plate dissipation and compare it to this chart. And depending on what type of amp it is, grid biased or cathode biased, we'll see if the tubes are biased correctly, if they're too hot, too cold, and then we'll also cover how to adjust that if they're not correct. Here's the amp we'll be using for this demonstration. It's a really nice old 1954 National Deluxe amp. You just gotta love this grill cloth. And this is the national emblem. Looks like a Route 66 emblem to me. Okay, so let's turn it around and I'll open the back. And before I do, I just want to remind you this would be a really great time if you haven't watched the first and second videos in this set. The first one covers biasing single-ended amps and covers a lot of basic theory. The second one covers the theory behind biasing this amp, and you really would gain a lot if you haven't watched those videos to watch them before you watch this one. All right, let's proceed. Here's the back of the amp before I pull off the rear panel. It's just such a nice amp. It has a really nice dashboard. Also, you know, you can tell if you see an older amp and it's covered with this tweed material. In this case, this one doesn't have the diagonal lines like the Fender does. This is the smooth. And the reason they did this, and it's almost always in the 50s when they use this material, is that's the way luggage was made. And I guess in their minds, we got a handle, it's sort of like a suitcase. Well, let's cover it with tweed because that's the way we cover luggage. Well, here's the rear of the amp with the back door off. As you can see, the chassis is fairly simple and real clean. Also, it has those 7x10 Rolla oval speakers, a pair of them, output transformer mounted down here. These speakers are virtually impossible to find in decent shape. You can't really recone them. So you operate amps like this at a very moderate volume to avoid any harm to these speakers. And that will affect my decisions in the plate dissipation values that I bias the amp at. Okay, let's take a look in the chassis and see what we're doing. Okay, these are 5881 tubes, and the cathode is pin 8. So we look over at pin 8, we see there's a yellow wire that jumpers to pin 8 of the outer 5881, and connected to that is this large cathode bias resistor. Now, I could use the first method that I described to you in the part 1 video, and that is jumper on one side and the other of this, measure accurately the resistance, then measure the voltage drop and calculate the average plate current for the two 5881s. Now, instead, on this particular amp, I'm going to individually check the plate current on each of the 5881s using the output transformer method. First, let me take a few seconds here to explain why I think that using the output transformer method to determine the individual plate currents is better than using the bias resistor to determine the average of the two. Okay, let's consider this scenario. First off, let's say that 40 milliamps is the proper plate current for a 5881. Now, what if this one were flowing 60 milliamps and this one's flowing 20 milliamps? If we used the bias resistor method and got the average, 60 plus 20 is 80 divided by 2, we would think that the plate current was ideal in these tubes at 40 milliamps. But instead, this one would be 60 and way too hot. This one would be 20 and way too cool, but we would not know that if we used this method. And if we accepted this value and allowed the amp to persist like this, we'd probably end up burning up this tube and, in the long run, having a really lousy tone from the amp because of the gross mismatch between the two tubes during the push-pull process. Using the output transformer method, however, we would quickly see that this was flowing 60 milliamps, this was flowing 20, and we could either change tubes or alter the bias of the tubes to balance them. Now, how that's done is this. Instead of allowing them to share the same cathode bias resistor, what I would do if I were confronted with a 60-20 split here is I would remove this cathode bias resistor because it really doesn't suit either of these, and I would put in a much higher resistor on this cathode and a lower resistor on this cathode, and there's a trial and error process here, but I could bring these both back around to 40 milliamps of plate current and virtually identical plate dissipation. One other consideration if you do that is if you have a cathode bypass capacitor, say like a 25 microfarad at 50 volts that is in parallel with this the bias resistor, you would then have to put one of those across each of your new bias resistors. So you'd have to have 125 here and another 25 over here. That said, let's get started on the procedure. This amp has not been plugged in several weeks. It's definitely not plugged in now, and it's not turned on. So while it's in this state, I'm going to use the method that I showed you in the single-ended video, and I'm going to drain these filter capacitors to be sure that they're not storing a charge. If any of you think that I go to ridiculous extremes on these, I remember there was an old cowboy movie called The Quick and the Dead, meaning you're either one or the other. Okay, well, I would paraphrase that dealing with amplifiers and say you could have two types, the careful and the dead. And I'd prefer to be in the former rather than the latter group. So now I'll demonstrate this once, but I'm going to do it repeatedly throughout the procedure. I'm going to clip one end of my jumper cable to a chassis ground, and then I'm going to go in with my resistor and touch the lugs of the filter capacitors and hold it there for a count of 10. Now that I'm satisfied that they are drained, I will continue. Now, since I've never been able to find a good schematic for this amp, I'm going to use my own diagram here as a schematic. And we're going to first measure the resistance between pin 3 of the outer 5881 and pin 8 of the rectifier. And that will give us the resistance right here of 1/2 of the output transformer. Then I will do the same with the pin 3 of the inner 5881 and the pin 8 of the rectifier and determine the resistance of this half of the winding of the output transformer. Okay, now I'm connected from the plate of the outer 5881 to the pin 8 of the rectifier, and it looks like I have around 220 ohms of resistance. I'm going to write that down. Now I'm connected to pin 3 of the inner 5881, and the other test lead remains connected to a pin 8 of the rectifier. It looks like I have about 195 ohms of resistance, which I will write down. Now, with the test leads in the same position they were on my second measurement, that is pin 8 of the rectifier, pin 3 of the inner 5881, I'm going to plug in the amp to a current limiting device, which you must have for safety. I posted a video to show you how to make one of these if you don't have one. You really need to have one if you're going to do work like this. Then I'm going to set my ohm meter, voltmeter down to DC volts and switch on the amp. Let the voltage stabilize. It looks like the inner tube voltage drop has settled down around 7.22, which I will write down. Turn off the amp, unplug it, and drain the filter capacitors. Now, working one-handed with your other hand in your pocket, move your test lead from pin 3 of the inner 5881 to pin 3 of the outer. Plug in the amp. Set your meter to DC volts. It should still be there. And turn it on. It looks like the outer tube voltage drop has settled down around 9.65 or so, which I will write down. Turn off the amp, unplug it, and drain the filter capacitors. Now we're going to measure the plate voltage of the outer 5881. I leave my red test lead on pin 3, which is the plate, and I take the black test lead off of the rectifier and attach it to the chassis, to a good, bare, unpainted chassis ground. Then I'm going to set my meter to DC volts, plug in the amp, and turn it on. Plate voltage on the outer 5881 is settled down to about 356, which I will write down. Turn off the amp, unplug it, and drain the filter capacitors. Now, using one hand with the other one in the pocket, we change the red test lead from the outer 5881 to pin 3 of the inner 5881. Plug in the amp, turn it on, and we will measure the plate voltage of that tube. The inner tube plate voltage is settled down to around 360, which I will write down. Okay, let's analyze the data that we got from our measurements. Outer tube, the resistance through the output transformer was 220 ohms. Voltage drop was 9.65 volts. You divide this by this, and you get 0.0439 amps, or 43.9 milliamps, which is actually a decent amount of plate current for this tube. Remember, we said probably around 40 to 45 is about right. We found the plate voltage on the outer tube to be 356 volts. We multiply that times 0.0439, we get 15.6 watts. Let's look at the bottom tube. 195 ohms of output transformer resistance. Voltage drop across at 7.22 volts. When we divide the voltage drop by the resistance, we get 0.0370 amps, or 37 milliamps. A little bit low, but still within acceptable limits. Plate voltage, 360 volts, times 0.0370 amps gives us 13.3 watts. Now, these do not agree exactly, but these are pretty close. If this were 25 and this were 15 or 12 or 10, I would start getting a little concerned. Now, these tubes agree fairly well. 15.6 and 13.3 are close enough that this would be an acceptable match. The average is 14.5 watts. Now, when we come down here and we see that 5881s can handle up to 23 watts, with probably around 20 being okay, 70% value on them is 16.1. This is definitely cold. This would probably be better if it were around 16 or 17. So there's two choices to be made here. Leave it alone, and because it's an old amp that's never used at very high volumes, you would get probably decent tone at low volumes, and you would get some early breakup at moderate volumes. So cold bias might suit this amp. The other possibility is if you want to goose it up to around 20 or so watts of plate dissipation, then what we can do is go in here and alter the value of the cathode bias resistor. And let's go from 250, this is 250 ohms, go down to 200. And then repeat the process. And I think you'd end up here with a value closer to 20. One last little interesting tidbit here. Compare the results that I just got using the output transformer method with a 14.5 watt average. I also ran, just to see how they would compare, bias by the cathode bias resistor method. And this is the result I got for the average of the two tubes, 14.68 watts. So it's around 0.2 watts higher than the output transformer method. And as I told you, this method almost always yields a slightly higher result. But the fact that they agree so well makes me believe that the results are accurate and reliable. And finally, let's briefly discuss how you adjust the bias on amps that are grid biased, in which the cathodes are connected together and taken straight to ground. Now, this is a rather complex issue, and I'm going to suggest that you might check on the internet for specialty sites where they go into great detail on how to adjust the bias on your grid biased amp. I will go over it rather superficially here, but if you want great detail, you're really going to have to check into specific sites. First off, we'll look at a deluxe reverb Fender amp. Now, as you can see, the cathodes are bound together and go to ground. So there is no cathode resistor here for us to adjust. Instead, we follow the grids out here. We follow them down and we see that there is a potentiometer provided in the chassis for us to adjust the bias of the deluxe reverb. If you look at the layout of the Deluxe Reverb chassis, and you can also look up layouts on other Fender amps, you'll see that this right here is the potentiometer. It's located right in the chassis. You will do your biasing procedure, take your measurements, and determine if it's okay. If it's too high or too low, then you will adjust it using that potentiometer. After you've adjusted it a bit, you can recheck. A little bit of trial and error is called for, but you can get it to be exactly right using that potentiometer. Other Fender amps like the Fender Bassman also have the potentiometer located in the chassis to assist you in your biasing procedure. Now, one real challenge presented itself recently when I was restoring a couple of Princeton reverbs. Now, if you look at the Princeton reverb, cathodes are bound together, go straight to ground. We follow our grids out here. They come to a resistor network. They drop down, and it goes to not a bias adjustment, but the intensity control of the tremolo. So, to be brutally frank, there's really almost no way to adjust the bias of a Princeton reverb amp without seriously affecting the tremolo. So I came up with my own way of doing it, and that is I came in right here and I ungrounded the cathodes, and you can start off with like a 100 ohm resistor to ground for each of your cathodes, or you can have them share a 100 ohm resistor to ground if you wish. But try that. Now, I only suggest this if your 6v6s are biased way too hot, and I warn you, they probably are. I have never seen plate current and plate dissipation values on any amp like I did on a Princeton reverb amp. Okay, so in my case, to save my tubes, I actually converted it and turned it into a cathode biased amp by adding 100 ohm resistors to the cathodes of the 6v6s. You can bring them down then to reasonable levels of plate dissipation, and in my opinion the tone is still wonderful and your tubes are going to last. I show this modification in detail on the 2 videos that I posted for the Princeton reverb amp. Well, that about does it for this part 2 video covering biasing methods of double-ended amps. We covered a lot of ground, and you may have to watch it a couple times for it to all make sense. Please, if you have any questions, feel free to ask them. But sit down and think about it. There's some of these things require a little active study and consideration before they become clear. So while you're doing that, I'm going to bid you a fond farewell. I appreciate your time and interest. I hope you'll subscribe if you haven't already. But no matter what, I hope you stay tuned and that I will see you again in the near future. Thank you so much.